We talked in part one, or at least I talked, about a few things related to this topic of over-constraint, how to recognize it, how to avoid it, and even a little bit about those of us who seem to relish in it. I started out by talking about CAD-itis, a funny term for when our parts look fine on CAD, but turn out to be a real pain when we try to put them together. I speculated that a leading cause of CAD-itis must be over-constraint, which is characterized by parts having more than one natural position in which they want to sit, parts becoming stressed and deformed when they're bolted together, and very tight tolerances required to mitigate the stress and deformation. I talked about how some of the GD&T concepts can put us into a mindset where we're getting away from the over-constraint. And what a great thing it is when your parts fit together right, reliably, because you made sure that they work in theory first. So let's get into talking about some more parts and drawings, what works and what doesn't. Let's call this gray part a sliding mount. It slides along the blue part, which we'll call a rail. The rail in this case has two V grooves and a row of threaded holes up the middle. The gray mount has a slotted screw hole that's long enough that you can slide this mount along, and then if you needed to, remove the screw and index to the next hole. The gray mount does not sit flat surface to flat surface on the rail. Instead, in this case, there are two precision pins that ride in the V-grooves. The pins are pressed into undersized, partial holes in the gray mount, if you follow me. Now, all these pins and grooves and tangential contact, if it's what we need, then we love it. But it sure is a way to generate a lot of constraint quickly. So let's have a look at this drawing. This is GD&T 00547. All right, so here we can see that this part consists of two items, the aluminum bulk material and the two dowel pins. I know that I really want to use these pins as datum features, and I will be at pains to do so. But first I'll have to locate the pins, which I'll do with these basic dimensions and with this position tolerance that has no datum reference yet. This ties together these dowels so that their axes must be within imaginary 4 thousandths diameter cylinders. And these imaginary cylinders are perfectly parallel to each other and exactly 1.5 inches apart. I would say that this 4 thousandths is a tight tolerance and probably difficult to inspect as well, especially given how little of the surface of the dowels is exposed. But we'll just leave that question aside for now. And look, there may be more practical ways to do all this dimensioning and tolerancing, at least from the inspection point of view, but for now, please just bear with me. For this detail view, I scale up on one of the dowels so I can show how I'm thinking about them as datum features. I have these kind of unfortunately difficult to see phantom lines with an angle and a dimension to their intersection point. The phantom lines look a lot like the V groove in the blue part, right? So with these phantom lines and the datum targets, I'm saying that the actual datum features are some line contacts that go down the length of the dowels and that are meant to develop when this thing sits in a datum simulator. And it would be a datum simulator of A-B, an equal precedence datum, so the simulator would have two V grooves. Pretty complicated, pretty unusual. But first, look, I drew a red box around this position tolerance. That 4 thousandths is pretty tight, but it still describes a tolerance that, in the context of this mount, might still make it pretty finicky and difficult to use. This thing probably looks pretty good to the casual viewer. A nice smooth ride, like it's on rails. And whatever you're attaching to this, it seems like the intent is that it stays in the same position as you slide this thing back and forth. Just to help you think about it, let's put in this part I'll call an aperture. I'm always going back to the aperture idea for these examples. It's simple and I can show you what I'm talking about. If I'm looking straight at this thing, I can say this sketch here is the nominal position for this hole when it's all assembled. And so in addition to staying aligned while we slide this forward and back, it's probably also nice that this be repeatable, as we call it. So when we do have to take out this screw and index to the next threaded hole, it comes right back into position. And so I'd say going into this, we know we're going to need some precision. The question is how much? Let's look at what happens if the pins are set a little wide within their tolerance. We end up with one pin wanting to sit nicely in contact with both sides of one of the V-grooves, but we're popping out on the other end, only in contact with one surface on this V-groove. And then up at the aperture, of course, we can see that we are off target. Now, of course, this thing would have another natural position, let's call it, which would be the opposite. We would have two surfaces contacting this dowel and only one on this dowel. And there are probably also these transitional positions where each pin is only sitting on one surface, which would always be unstable. These effects would be seen not only if the dowels are set wide, but also if they're set narrow, or if the V-grooves are set wide or set narrow. Further, we know fundamental rule number one is that all features have tolerance. We know that these dowels have to have a position tolerance. We know that the grooves in the blue part have to have some kind of position tolerance. And because of that, we know that there will be positional deviation between the dowels and between the grooves. The position tolerance also allows for some deviation in the parallelism of the dowels within the tolerance zones. Let's look at some illustrations of that. In this example, one of the dowels is kicked out at a small angle in this rotation here. So what happens when we place this one on the V-grooves? Maybe as expected, one dowel is sitting nicely on both sides of one of the grooves, but on the other end, we're lifted up and we're only making point contacts on either end of the pin. And up top, our aperture is out of position. And this is another example where we could just as easily have two surfaces in contact on this dowel, and then on this end be lifted up with just the 2 point contacts. So two natural positions for this thing, and of course, all the transitional stuff in between. And in case you haven't guessed already, given the topic of these videos, the reason all this bad stuff is happening, the reason we would still see these problems even as the tolerances approach zero, is because the design with the two dowels and the two V-grooves is fundamentally over-constrained. When I think of a dowel, a cylinder, lying in a V-groove, I think, that's a 4 degree of freedom constraint. In the biz, we call it 4-DOF. If you look at this equal precedence datum AB and how I described it, it's like we're trying to build a primary datum off of two 4-DOF constraints. This datum reference, in all of its complexity, is a warning to you as you're making this drawing that things are not good. Look at this position tolerance here and realize that it is in contradiction to the datum simulator, which is in basic position. And so we can dampen or mitigate the effects of over-constraint by tightening this tolerance even farther, but we can only go as far as our manufacturing process will allow. But the real way to deal with over-constraint is to remove constraint. And so here we have our same mount again, only now in the rail, we've replaced one of the V-grooves with this nice flat bottom groove. This way, if we inevitably have a dowel that is rotated a little bit, it doesn't really bother us too much. Similarly, if the dowels were set too wide, that wouldn't affect us very much either. We're off on the aperture up here, but my plan anyway was that we would loosen these screws and move this aperture around on these giant washers anyway. If we were going to use the mount this way, I would want to do the drawing a little bit differently. So let's go to GD&T 00548. This is similar to 547 to a point, okay? But over here on detail A, I show the V-shaped datum targets on one dowel, and then on the other dowel is just a single surface, like how it's being used in the blue part. Now I'm feeling a little bit like I can call datum A a primary datum and datum B a secondary datum in these feature control frames. I was talking earlier about a dowel laying in a V groove as a 4-DOF primary datum. So that's A. With this dowel loaded into the V groove, we're only free anymore in and out of the page and rotating around that dowel, around datum A. So what does datum B do? Well, it would only constrain us in that rotation around the dowel. It wouldn't do anything to constrain us in and out of the page. So is the second dowel a 1 degree of freedom datum feature? When I think of a dowel laying on a flat surface, that sounds like 2-DOF to me. Let's call it translation in Z here and the pitch. But the pitch is already constrained by datum A. This all makes sense when you consider that you are not going to get perfect line contact down the length of the second dowel. And that's because, invariably, the dowels will also be out of parallel in this other rotation. I can really see this one happening. What does it look like when we place it on the rail? Well, it seems like it would want to rock diagonally. And if we held one of the dowels down into the V groove on this side, on the other side, it'd be lifted up and only have one point of contact on one end of the dowel in the flat groove. And because it's lifted on one side, our aperture, of course, is off target. This gray mount part is pretty thick, but what if you could tighten that screw so much that you could twist the part and force that right side dowel down into the flat groove? Maybe then the aperture would come back into its correct position. But that would actually make this a pretty frustrating mechanism. You would get everything all aligned, and then when you tighten the screw, it moves on you. Not to mention all the stress you'd be putting into the gray part and the blue part. Not to mention that as you tighten that screw, it's just gonna like mush as it's bending and forcing all these things. It's never gonna feel right. Let's have a look at the drawing GD&T Guy 00549 now, which just sort of acknowledges that we're only gonna have one point of contact in the flat groove. And we're going to do that by replacing the second dowel with a ball. This is getting to be pretty good, okay? We're getting closer to having a kinematic mount. Really, my only remaining criticism is that we still haven't taken into account the straightness of the dowel or the straightness of the V groove. And to deal with that, the last thing left to do would be to replace the remaining dowel with 2 more balls. And I'm sorry to say I did not finish the drawing for this one. Maybe I'm getting tired of all these little variations. It would have been called GD&T Guy 00546. Try to use your imagination. I don't think it'd be that much different from 549. But now when we look in the assembly, this has become what I would call a properly kinematic mount. Highly repeatable, doesn't rely on any tight tolerances at all, except for maybe the press fits. But you could even go to bonding for these balls. One more little thing to mention is that we're now down to 5 little point contacts where the balls meet the grooves. I would worry that we could end up Brinelling the surfaces when we tighten the screw. The harder the material of the blue part, the larger the radius of the balls, the less Brinelling will happen. But just to make a point of it, I replaced the socket head cap screw I was using with this shoulder screw and some Belleville spring washers. This is just to reduce and control the preload and prevent that Brinelling. I can imagine some of our over-constraint loving engineers looking at this and thinking, geez, I would have just kept the screw in there and jammed this whole thing together. The Brinelling sounds great to me. Well, the problem with that is that if you ever needed to slide this thing again, ever so slightly, you could forget about it because the part would always find its way back into those Brinelled seats. But let's stay focused on the big upshot here. This thing is going to perform great, and the tolerances are no big deal. I would venture to say that this mount with the 3 balls, if we were using the rail with the V groove and the flat groove, even if this were made sloppily, it would still outperform this mount with the 2 dowels if it was made extremely precisely. This would have to be made extremely precisely to slide back and forth and to be as repeatable as the design with the 3 balls. Think about it. These balls could vary in their positions, in their various levels of protrusion. It would still register great in there. All right, let's get away from these sliding mounts, finally. I have one more set of illustrations that I want to show you on this topic of over-constraint, at least for now. Okay, so this one is a somewhat elaborate assembly with a special housing. This is actually a little similar to how we started with that brace part that had the two competing primary datum features at 90 degrees to each other. Remember that? It might be another one where some of you are saying, hey, looks all right to me. It has this relatively thin base plate here, and then these two shell-like housings that attach on top. The base plate has these 4 screw clearance holes out in the corner that we're going to use to bolt this thing down at some higher assembly level. And on the bottom here, we can see some features for an electrical connector. Also on the bottom, we can see some counterbore screw holes that go up into the larger of the two housings. I guess under this housing here, there are some components, but I didn't get so far as to build this all out, okay? And then we have this second, slightly smaller cover that attaches to the base plate and to a 90-degree surface on the larger cover. Under this one, we have a circuit board that's screwed down to the base plate at several locations. Maybe it's safe to say that the reason the two covers attach differently is because we want the circuit board to be accessible in the field. But then we want to discourage someone from accessing whatever is under the larger cover. Let's just go with that. You can see that I have an O-ring lightly packed into a gland that goes all the way around. And I guess it wouldn't make a perfect seal here because the way these things join in the corners. All I can say is this is far from a perfect design. What I want you to think about here for now is this circuit board here. The reason I like this for this illustration is because, well, for one thing, I design a lot of circuit board housings, but also just because the construction of a circuit board. These are laminated layers of fiberglass and epoxy with copper traces. This circuit board would have surface-mounted components. I didn't model any of them in here, with little tiny solder joints and sometimes little wispy wires going from point to point. What you really don't want with a circuit board is a lot of flexing and bending. It'll fatigue all those joints and the laminated layers. A circuit board can be spec'd for flatness, usually some rate of flatness over so many inches. But like everything, it's not perfectly flat. And pretty often we do want to support them with a good number of screws, maybe to keep it from vibrating too much. But when we do that, we're forcing it into conformity with the nominally coplanar, standoff-like features in the base plate. But if you got to do it, you got to do it. Okay, and now we put on our cover. Remember back to the brace part that had two competing bolt interfaces at 90 degrees to each other? Back then, I talked over some of the same problems we're going to see in assembly here. But they're only going to be worse in this case, at least because of that O-ring, which is going to create friction and stickiness in these joints. And that's going to be a pain because you're going to have to sneak up on this thing, tightening up the screws ever so gradually so that you don't end up with a gap. O-rings usually need to be compressed 20 to 30% of their cross-sectional diameter in order to be effective. That compression is controlled by the depth of the gland or the groove that these are set into. We're looking for metal-to-metal contact between the flanges to finish the job. So a big thing we should be worried about is what's going to happen if we don't have a great 90 degree to 90 degree matchup between these parts. And then what's going to happen if we try to close that gap by tightening the screws. And these housings, even though the walls are thin, just because of their height, they're going to be so much stiffer than the base plate, and they're going to bend that base plate up. And the circuit board is going to bend right along with it. Sorry about the depiction of the screw heads here. Okay, so now our circuit board is stressed pretty bad. Maybe we didn't see this coming. If we were doing the drawing for this base plate, we're going to put a coplanarity control on the tops of all these bosses. Not to mention a flatness on the bottom surface. But all of that is moot if this base plate gets stressed and deformed in this assembly. Our circuit board is just going along for the ride, okay? All right, so the base plate and the circuit board are stressed, but we got this assembly bolted up and ready to deliver. So what happens when someone takes this and bolts it up to a flat surface in the next assembly or out in the field? And they tighten down the mounting bolts, maybe pretty big ones, into the 4 screw holes in the corners. Well, it's going to stress the assembly back the other way, including the circuit board. Maybe all that force is too much for the smaller screws holding the housing together, and they fail. At any rate, it's going to be a weird build because it's not going to sit right, and it may not ever feel like it's bolted securely with a gap under here and the housing acting like a spring. Okay, let's keep going with our story. Now it's attached to its host, it's out in the field. What happens when we remove the cover and try to service the circuit board? Well, the base plate is going to snap back into flatness, and the two mounting screws on this end are going to be loose now. Maybe somebody notices that while they're working on this thing and they decide to snug them up while this cover is off. They do their work on the circuit board and they put the cover back on. Now we have this gap and we lost our seal, but who knows if the technician in the field is even going to notice that. We aren't really doing them any favors with this design. I have a drawing here. This is GD&T 00550, which is for our base plate. Here we're calling out a flatness for the bottom surface. And then in this callout, we're relating the surface to which the housings attach with profile and then controlling them with flatness. And then it's pretty much the same thing here for the tops of the bosses to which the circuit board will attach, only now it's profile and coplanarity. So this is good, and we can do this on the drawing, but for this surface to remain flat and for these surfaces to remain coplanar, it only works if the part is not forced into bending, right? Well, we do have another card we can play in this situation, which is that we can add relief. So this is drawing GD&T 00551. And you can see now that the part has this large but shallow relief on the mounting surface. The major difference on the drawing here is that I changed the flatness to a 2x coplanarity, and I tightened it up quite a bit because without all this material in the middle, this is a much more forgiving tolerance. I love this term relief in this context. It's going to take all this over-constraint and stress, and it's going to relieve us of it. Because even if it is bent and distorted by the housing parts, when we set it down on a flat surface, all the contact is going to be out on the ends here by the mounting holes. When we go to bolt down our subassembly, we aren't going to have to bend it about some contact in the middle here, right? Any stress is going to be much more localized out here around the mounting holes. I hope we get to talk about relief a lot more in the future. It wouldn't solve the problems associated with bolting up the smaller cover on that over-constrained 90-degree interface. But it could help with some of the other problems that would come later when this subassembly is integrated into the next assembly. Really, even though it is nice looking in a turtley sort of way, this design needs to be reconsidered. I would say almost always the thing to do would be to make the base plate thicker and therefore stiffer compared to the covers. And if anything can be done to reduce these covers to a simple, flat panel with a single planar sealing and bolting interface, that would be an improvement. Okay, great. I hope you have the energy for one more set of illustrations that will help with this topic of over-constraint. This is a whole new assembly, okay, but it borrows some ideas from the last one. Let's say we have this blue frame part that has 6 mounting locations to the next assembly. And then it's largely hogged out with these big pockets into which we're going to place these green subassemblies. And let's say that the green subassemblies have circuit boards inside that we don't want to stress too much. And maybe we'll just say that we're in the conceptual phase of this project, where we're still trying to settle on construction and how all these parts are going to attach to each other. You know, we saw this in the last assembly too, but we largely live in a world of squares and rectangles. Squares and rectangles have 4 corners, so it's extremely common to see engineers and designers go directly to 4 screws for something like this. Okay, but it is 3 points that make a plane, not 4. And anybody who's ever sat on a 4-legged stool knows that one of the feet is always up in the air, and you end up rocking back and forth between 2 positions. And it's the same thing here. When we go to tighten the 4th screw, it is going to have to close a gap by stressing either the green subassembly or the blue frame. When you attach on 3 points, you either don't have that problem or it's greatly diminished. I've seen over-constraint loving engineers run in the opposite direction with this. They want to attach at multiple points to tie this housing together, even if it means putting holes through their circuit boards and their housings to get there. The appeal of this idea seems to be that we're going to create a stiffer, more robust structure this way. What I would say to that is to imagine this frame being mounted on top of 6 posts, and then to imagine those posts pistoning up and down randomly and independently. Okay, and that's probably what vibration will look like as it propagates through this system. Whatever bending and twisting the blue frame goes through, it's going to transfer that energy into the green subassemblies, into the circuit boards, into the solder joints. And the same thing happens, maybe to a lesser extent, with the 4-screw design. What happens when this point and this point go up, and this point and this point go down? The green subassembly is going to be forced to bend and twist right along with it. Look at it now with the 3-point mount. If opposite corners go up and down, well, sure, the green subassembly will move, but it should not be forced to bend and stress, except maybe right locally near the mounting points. And I would also say to the over-constraint loving engineer that these points seem to be pretty well supported, even though these in the middle are not out by the corners. It shouldn't take a multitude of screws to provide enough preload to secure this thing. I would rather use 3 larger screws than 8 smaller ones. All right, I think that's the last thing I have to show you for this. I hope it all made sense and that you got something out of it. In the making of this video, I now have more ideas for spin-off videos in the future, but we'll cross that bridge when we come to it. But I think it's a lot of fun because this is really the intersection of GD&T and design. I think it's a great thing for me to do with this channel to show how GD&T will make you a better designer. All right, that's all for now. We'll see you next time.